Have you ever wondered how a massive steel ship can just float on water? Or how a giant airplane seems to defy gravity? Well, the answers are all hidden in the invisible forces that govern the fluids all around us, from the air we breathe to the water we drink. Today, we're going to pull back the curtain on the absolutely amazing mechanics of liquids and gases.
All right, let's dive right in. Before we can really get into how fluids behave, we first need to get a handle on what a fluid actually is. And believe me, it's more than just being wet. So, what's the big difference here? Well, look at a solid, like a block of wood. It holds its shape, right? But a fluid, it'll take the shape of any container you pour it into. The real test, though, is how they deal with stress. If you push on a solid, it pushes back. But if you push on a fluid, it just moves. It flows. And that right there, that's its superpower. Okay, let's get into our first huge concept that really dictates how fluids work: pressure. Now, it's a word we throw around all the time, but in physics, it has a very specific and very powerful meaning. Think about this for a second. You've definitely experienced it. You can push with the exact same amount of effort with both a knife and a spoon, but you get completely different results. The answer to this little puzzle gets right to the heart of what pressure truly is. See, it all comes down to the concentration of that force. Pressure is simply the force you apply divided by the area you apply it to. A sharp knife focuses all of your effort onto a tiny, razor-thin edge. That creates incredible pressure. The spoon, it spreads that exact same force out over a much wider area, which means low pressure. That's why it just makes a dent. And what's really wild is something a French scientist named Blaise Pascal figured out. He realized that inside a contained fluid, pressure isn't just in one spot. When you apply it at one point, it gets transmitted everywhere inside that fluid, equally and without losing any strength.
And this simple U-shaped tube shows Pascal's law in action perfectly. This is the secret sauce behind all hydraulic systems. You see, you apply a small force to a small piston, which creates pressure in the fluid. That pressure then travels through the fluid and pushes up on a much larger piston on the other side. So check this out. Because pressure is just force over an area, if that second piston has an area 9 times larger than the first one, the force gets multiplied by 9. It's amazing. This is how a simple push can be enough to lift something as heavy as a car. It's literally a force multiplier, all powered by fluid mechanics. Okay, but it's not just about pushing from side to side. There's another huge factor at play here: gravity. Pascal's law is true at any single depth. But as you go deeper into a fluid, the pressure increases. And why is that? Well, you've got the weight of all the fluid above you pushing down. I mean, get this. If you swim just 10 meters, that's about 33 feet below the surface of a lake. The pressure acting on you has already doubled. You're feeling the weight of the entire atmosphere plus the weight of that 10-meter column of water. So far, we've been looking at fluids that are just kind of sitting there, right? Fluids at rest. But things get really interesting when they start to move. So let's dive into the secrets of how fluids actually flow. You know this one. You've totally seen this in action. When you put your thumb over the end of a garden hose, what happens? The water shoots out way faster. That is not a coincidence. It's a fundamental rule of fluid dynamics called the equation of continuity. This diagram shows it beautifully. Look, the same amount of fluid has to get through both the wide part and the narrow part in the same amount of time. So to make that happen, when the pipe gets skinny and those streamlines you see there get squeezed together, the fluid has no choice. It's got to speed up. And this connection, this link between a fluid's speed and its properties, it's not just some neat trick for garden hoses. No way. It is the secret behind one of the most incredible inventions in human history: the airplane. The secret is Bernoulli's principle. Now, I know the official definition on this slide looks a little intimidating, but the core idea, the main takeaway, is actually super simple. For a flowing fluid, where speed is high, pressure is low, and where speed is low, pressure is high. They're like a seesaw. When one goes up, the other goes down. And this one principle is incredibly powerful. It's what creates the lift on an airplane wing, sure, but it's also the exact same reason a spinning baseball curves through the air. You might know it as the Magnus effect. The exact same physics is at play in both situations. So let's take a look at an airplane wing, or what engineers call an aerofoil. Its shape is absolutely not an accident. It is meticulously designed to force the air flowing over it and under it to behave in very, very different ways. Okay, so here's what happens. That curved top of the wing forces the air to travel a longer path, so it has to speed up.
The flatter bottom lets the air underneath travel a shorter path so it moves more slowly. And remember Bernoulli's principle? That faster-moving air on top creates a zone of lower pressure, while the slower air below creates higher pressure. That pressure difference results in a net upward force. And that, my friends, is lift.
Let's actually look at the numbers for that Boeing. The curved shape of the wing is called an aerofoil, and it's designed to force the air to travel faster over its top surface than its bottom one. Now, to lift 330,000 kilograms, how much faster do you think that air needs to go? You'd be surprised. The air above the wing only needs to be about 8% faster than the air below it. That small speed difference creates enough of a pressure difference to make the entire plane fly.
Now, Bernoulli's principle is based on an ideal fluid, a perfect one, with no friction. But in the real world, things are always a bit messier. Real fluids have their own kind of internal friction.
And we call this property viscosity. You can basically just think of it as how thick or syrupy a fluid is, how much it resists flowing. So honey, for example, has a really high viscosity, while water has a pretty low viscosity.
And the range of viscosity between different fluids is just incredible. Take a look at this chart. Blood is already more than twice as thick as water, but then you get to something like glycerine, and whoa, it's over 800 times more viscous. That's a massive difference in how these fluids are going to behave.
All right, our final property explains something that honestly just looks like magic. How can some insects walk on water? And why do raindrops form those perfect little spheres? The answer is an invisible skin that all liquids seem to have.
This phenomena is called surface tension.
Imagine a molecule deep inside a glass of water. It's being pulled on equally from every single direction by its neighbors. It's perfectly balanced. But a molecule right at the surface, it doesn't have any neighbors above it, so it's only getting pulled inwards and sideways. This constant inward tug gives the molecules on the surface a little bit of extra energy.
And this extra energy at the surface leads to a really cool question. Have you ever wondered why free-falling raindrops, or even soap bubbles, naturally pull themselves into a perfect spherical shape? The answer is actually pretty elegant and simple. It's because nature is, well, kind of lazy. It always wants to be in the lowest energy state possible. And since those surface molecules have extra energy, a liquid will always try to have the smallest possible surface area. And for any given volume, the one shape that has the absolute minimum surface area is a sphere.
So we've covered pressure, speed, friction, and tension. Let's pull it all together now and see how these invisible forces have some very visible and very important effects on the world all around us.
So here's the big takeaway. Pascal's law gives us these incredibly powerful machines like hydraulic lifts and even the brakes in your car. Bernoulli's principle is what lets us fly, and it explains the wicked curve of a spinning baseball. Viscosity is essential for our own bodies and for our machines. And surface tension, it's what shapes a simple raindrop and even helps water climb up inside of plants. You know, everything we've explored here is really just the beginning. This entire field of study, how fluids move and behave, is called fluid dynamics. And it is a vast and absolutely fascinating area of physics. Which really leaves us with one final thought. We've seen how just a few fundamental rules of physics can explain things that look, for all the world, like magic. Lifting a car with your foot or making a metal tube fly through the air. It just makes you wonder, doesn't it? What other everyday magic is out there, just waiting for us to understand the physics behind it?